Thank you all for joining us for the third session in this four-part course, which is hosted by the Faraday Institute of Science and Religion and funded by the John Templeton Foundation. I'm William Simpson, a junior research fellow at Cambridge and the organizer of this online course. Before I introduce today's speaker, I think it'd be helpful to look back over the previous two sessions and bring to mind some of the important ideas we've covered. We began our discussion with a shared sense of dissatisfaction with the microphysicalism that dominated the philosophical landscape of the last century, which seemed to leave little space for human beings as rational and free agents. We've been thinking about general accounts of reality, which can incorporate what the sciences are telling us about nature, but can also make sense of the possibility of human beings having such knowledge. In the first session, Brian Pitts, a senior research fellow of the University of Lincoln, defended the coherence of Descartes' dualistic division of reality into material things and thinking things, and brought us up to speed with contemporary discussions concerning the famous mind-body interaction objection to dualism. Such misgivings often take the form of an energy conservation objection, in which dualism is said to violate the conservation of energy that is supposedly demanded by modern physics. From Brian, we learned, however, that conservation laws are conditional laws which are tied to mathematical symmetries. Anything which makes a difference to how the physical stuff in a system behaves, in the sense of breaking the time symmetry of whatever physical laws are supposed to apply to that stuff, will violate energy conservation. But time symmetry only holds given the absence of any external influence on a physical system, and establishing the absence of such influences, Brian argued, is an empirical question. Simply invoking conservational laws against dualism is begging the question. Michael Esveld, a professor of the philosophy of science at the University of Lausanne, agreed with Brian's rebuttal of the interaction objection, but argued that the real problem for incorporating human persons into our picture of reality is a conception of laws and their initial conditions which predetermine everything from the properties of particles to the properties of people. Yet Michael believes a weaker form of dualism is sufficient to rescue persons from the clutches of physical determinism. In Michael's ontology, which he calls superhumanism, nature consists solely of matter points, which are nothing over and above the distance relations in which they stand. According to Michael, we get into trouble with quantum physics when we treat microscopic matter as having intrinsic physical properties. He thinks that all we need in our physical ontology to make sense of what the sciences are telling us is a particle configuration, and that all the dynamical variables which enter into our best physical theories merely summarize where all the particles end up. This means that the initial conditions of the world, which have to be fed into the physical laws to determine where all the matter ends up, are only fixed at the end of the world, so to speak, because they are not fixed by the intrinsic properties of any of the particles, but depend on how the particles are distributed over the whole of space and time. The initial conditions which feed into the laws take into account the free motions of human bodies in the here and now. Although Michael acknowledges, on the one hand, that the facts about particle positions are fixed up to the present moment, he insists, on the other hand, that the initial state of the world, as it is specified in terms of various physical parameters by our best physics, depends in part on what you and I are doing right now. Michael agrees with Brian that persons should be accepted as primitive in order to protect a space of reasons in which they are free to make rational judgments and act accordingly in the material world. Unlike Brian, he thinks that persons like matter points, which the matter points which compose their physical bodies, lack any intrinsic properties. The relational lesson in ontology, which quantum physics teaches us, according to Michael, should be applied across the board. It is sufficient to identify persons with mind points, which are nothing over and above the normative relations in which they stand. In short, then, Michael opts for a neo-Kantian view of persons. There are no Cartesian minds, but humans have freedom to act in the world in the sense of libertarian free will. He thinks that this freedom is a prerequisite for the possibility of doing science. Today, Robert Koons, a professor of philosophy at the University of Texas, will be pushing back against both the Cartesian dualism defended by Brian and the neo-Kantian dualism advanced by Michael, and exploring a pre-Cartesian conception of persons as unified substances, which goes back to Aristotle and which shaped Thomas Aquinas's conception of nature. Whereas Brian and Michael both seek to add something non-physical to a picture of reality in which all of the physical things that scientists investigate are composed of some set of microscopic constituents, Rob seeks to challenge the notion that physics picks out a single set of microphysical constituents and to provide hylomorphic analysis of physical things in which they have forms which determine the physical properties of their matter. I met Rob several years ago in St. Andrews while I was pursuing my first doctorate in physics and beginning to have ideas about how Aristotle's doctrine of hylomorphism might be used to make sense of the physics of complex systems. We've been talking about hylomorphism in physics ever since, exchanging papers and sharing ideas. And since then, Rob has done some very interesting work on hylomorphism and emergence in physics. And I'm delighted to have him with us this afternoon to tell you more about it. Over to you, Rob.
Great. Yeah, thank you. Thank you, William, for a great introduction. Let me see if I can share my screen and do my slides. Okay. And here we go. Good. Can everyone see that? Is that working?
Mm-hmm.
Okay, great. So as William said, I'm going to discuss some work that that he and I have been doing over the last 4 or 5 years. I want to thank the Faraday Center and the Templeton Foundation for sponsoring this series. I think it's a critically important topic for anyone who's trying to forge a harmonious picture of the world, one that incorporates our best physical science, but also leaves room for a richly humanistic and ultimately religious viewpoint. So I'm going to argue that the quantum revolution of the last century in particular has created the space necessary for the revival of an Aristotelian metaphysics and philosophy of nature, a pluralistic framework that's well suited for situating human beings within the natural world. So just a quick overview of the talk. I'm going to start with discussing the logical space of options for human agency in the natural world. Then as William said, I'm going to push back against dualism a bit in section 2, argue there's some ethical, epistemological, and ontological problems there. Then switch to the Aristotelian story, in which souls are substantial forms. So they're not really as unique as they would be under a dualistic picture. Every kind of substance has a substantial form. Then I get into the heart of this work we've done in section 4, where I talk about how quantum mechanics can make sense of the natural world, including inorganic substances. And then finally conclude with talking about the metaphysics of not only inorganic, but also living substances and ultimately rational animals, and how an Aristotelian picture makes room for all of that. So the logical space of options. The first issue is whether we want an extreme or a more moderate or pluralistic ontology of the material world. Now, by an extreme ontology, I mean one according to which only either the very small, the fundamental or indivisible particles, or the very large, the whole cosmos, counts as metaphysically fundamental. So an extreme ontology, I think, is going to be necessarily a physicalist approach to the material world, since particles and the cosmos are both non-living, presumably non-conscious entities, fully describable by the equations of fundamental physics. Now, in contrast, the moderate sort of ontology counts as fundamental some medium-sized composite objects, like you and me, for instance. This requires a pluralistic approach to natural sciences, one that refuses to privilege physics, especially particle physics, over other natural sciences like chemistry, thermodynamics, biology, or ultimately human sciences. In fact, as you'll see, I actually underprivilege particle physics. I think in a way it's the only non-fundamental science among these. So in any case, if we adopt an extreme ontology of the material world, we have 4 sub-choices on this slide as to where to fit in the human agent. One option would be to say there are no rational agents. There's no rationality, no consciousness at all. That's eliminativism. On the opposite extreme, you might say, well, maybe the material world itself is just constituted by mental states and events. So I'm going to set aside those two views because I think they're both counsels of despair in a way, failing to attempt to integrate our understanding of the physical world with the world of agents. So we'll focus instead on reductionism, that rational agency is constituted somehow by the behaviors and dispositions of purely material entities, and dualism, which is the view that, again, Brian and Michael defended, at least to some extent. On the other hand, among the pluralistic ontologies, in which some of the fundamental entities are both composite and smaller than the whole cosmos, medium-sized, we have two possibilities. One, which I'm calling standard strong emergence, in which both the microphysical and the composite entities are fundamental. So both I and my particles are fundamental. And an Aristotelian hylomorphism, which only the composite entities are fundamental. The parts are always dependent upon the whole. And I think those pretty well cover the logical space. Now, reductive physicalism. Here, there's a common ground among all three of us, of the lecturers. We all reject reductive physicalism because we think that it doesn't really leave adequate room for human agency and for human rationality. So first of all, there's the problem that reductive physicalism puts human agency and epistemology under threat from bottom-up determination. If the particles and their motions governed by the physical laws determine everything, and there's really no room for human free will or for human rationality to make a difference. Human reasons and insights can't make an irreducible difference to human behavior without massive overdetermination, which I think would be unacceptable. And secondly, there's a problem. There doesn't seem to be any non-arbitrary, principled way of dividing up the physical world on this picture into discrete organisms and persons. So our very existence is beset by a kind of vagueness and indeterminacy on this kind of story. There isn't really room for us as entities in that picture. So let's turn to dualism, which is, again, the view that the other lecturers are defending. And I'm going to argue this has three sorts of problems: ethical, epistemological, and ontological. So the ethical problems have to do with the alienation of human persons from their living human bodies. So the bodies become external mechanisms that are not really integral to our human existence. Secondly, epistemological, I'm arguing that the dualist view involves a deflation of our manifest image of the world, our naive understanding of the natural world, and that creates epistemological problems for science in particular. And then finally, ontological. I'm going to raise a series of awkward questions for the dualist that I think make that an unsatisfying kind of position. So first of all, again, really quickly, some of the ethical problems for dualism. First of all, there's the problem of, these all again stem from excising the human body from the core of our human identity, right? So dualism treats the body as a kind of disjoint instrument, right, by which the soul acts on the physical world and from which it receives information. And this leads to a minimizing of the importance of the living human body, let's say before it gains that usefulness as an instrument, or after it loses that usefulness as an instrument. And I think this has very profound and negative implications for the protection of human life, both at its beginning and at its end. Secondly, dualism requires us to underestimate, I think, the moral significance of various kinds of assaults on the human body, like rape or torture, which have a moral significance for dualists only insofar as they affect the experience or the operations of the soul. Yet the moral significance of these kinds of violations of bodily integrity, I think, are not limited to such a narrow band of consequences. You know, think of the rape of a comatose patient, right, who's not going to recover. From a dualist point of view, there's really no harm there. And yet clearly there's something morally significant going on. Similarly, it can't really explain why something like a petametaphilia, the desire for amputating a healthy limb, should be solved by psychotherapy rather than by surgery, right? As long as both of them achieve the same kind of psychological equilibrium, what's the problem? I think ethically it's a real problem to violate the integrity of the human body in that way. And finally, I think the significance, the profound moral significance of sexual union or coitus goes far beyond its merely psychological or physiological consequences. And yet dualism can't explain that, can't really explain why this act has a special kind of moral meaning. Epistemologically, dualism has several, I think, serious epistemological costs. Dualists, like other physicalists, right, must deny that the secondary qualities, things like colors, sounds, smells, solidity, and so on, as we experience them. They must deny that these, as we experience them, are really features of the physical world. Instead, they're merely appearances in the mind, so to speak. And so even if there are extremely complicated, gerrymandered physical properties that sort of roughly correlate with our experience of secondary qualities, these properties are going to lack the kind of simplicity, uniformity, and intrinsic qualitative resemblance that's possessed by the secondary qualities as we experience them. But as the Irish philosopher George Berkeley argued long ago, if our perception of secondary qualities is wholly unreliable, they're not really there, this provides us with a defeater for all of our empirical knowledge. We can no longer be justified in relying on what's called phenomenal conservatism. That is the view that things are generally the way they appear to us to be. And this undermining of our naive faith in sense experience would undermine all of experimental science. And I'll argue later that the hylomorphic approach instead actually can preserve the veridicality, the reality of these secondary qualities. Moreover, secondly, dualists must concede that any causal laws that connect the physical world with the mind, with phenomenal qualia, let's say in particular, are extremely complex. And this means that we can't suppose that the correlated physical properties are natural or projectable. That is, they can't be the sorts of things that are reasonably part of an inductive generalization. We'll run into a version of Nelson Goodman's Grue-Boolean paradox, which we'll have time to talk about. We can talk about during the question period. But this means that we can't rely on inductive generalizations that are based, again, on these kinds of perceptions of secondary qualities. Finally, there's a number of ontological problems for dualism. First of all, just how far down the phylogenetic scale do dualists want to go? I mean, what are they going to do with non-human animals, I guess, and plants for that matter? How far, if we stop with human beings, then I think we're saddled with a implausible anthropocentricity, like Descartes treating all non-human animals as merely soulless mechanisms, right? That doesn't seem plausible. But if not, where's the natural place to stop? Do we want viruses to have souls and free will or something like that? I mean, it's really hard to see where they can stop. Dualists essentially sacrifice the unity and integrity of creation, I would say, requiring many essentially miraculous interventions by God to insert souls into the natural order and to keep the internal states of souls correlated with the physical conditions of their bodies. I mean, alternatively, we have to suppose that God empowers microphysical particles with the power to generate and ultimately to interact with souls. And this strikes me as implausible and would require a great number of very brutish, complex sort of natural laws that I think we should try to avoid. All right, so let's look at the Aristotelian option instead, in which souls are substantial forms. I'll first of all talk about what it is to be a substance, bring up a dilemma for the standard strong emergence view, which is the other kind of pluralist view that I'm going to reject, explain how hylomorphism avoids that dilemma, then get into the question about what the world's substances are and why they have to have something called substantial form, which we'll get to in section E. So first of all, what is it to be a substance? The Greek word for Aristotle, of course, is ousia. There's four sort of features here, which I want to emphasize. One is that substances are things that exist in the central focal sense of the word. So they exist in the most fully meaningful sense of the word existing. They constitute the uniquely fundamental level of created reality. So within creation, they're as fundamental as you get, substances and their states. They have per se unity. They're unified in the strongest possible sense, despite their having parts, despite their being composite. And they provide the principal ground within nature for change and persistence, and ultimately for the laws of nature themselves. So the laws of nature are going to be grounded in the natures of substances on this kind of picture. Now, as I said, the other alternative to Aristotelianism is what I'm calling standard strong emergence, in which both organisms and other substances and the fundamental particles are fundamental. In this view, substances like you and I contain independent microphysical substances, particles, as their ultimate constituents. And this leads to a dilemma. Is there strong top-down causation from the whole to the parts, to the particles, or not? If yes, then standard strong emergence is really just a variant of dualism, right? The so-called whole is really a non-physical thing that somehow interacts with these physical parts in a dynamical sort of way. If no, then standard strong emergence ends up being just another form of reductive microphysicalism. The whole ends up being just epiphenomenal, doesn't make any real difference to the behavior of the parts. So how does the Aristotelian hylomorphist avoid this dilemma? They avoid it by denying that the microphysical parts are independent in any sense. They deny that they have ontological independence. They are instead ontologically dependent on the whole substance. In fact, there are two kinds of parts in this Aristotelian story that substances can have: integral parts and virtual parts. And also there's some things that are both integral and virtual, as we'll see. So an integral part is something, X is an integral part of Y, just in case X is a part of Y. They're both material, and the nature is definitionally dependent on the nature of the whole. Part could not come into existence except substance, or in fact of the substance Y. So examples here from Aristotle would be things like organs, hands, eyes, feet, and so on, which, so the very nature of a hand, right, is such that it is a certain kind of a part of a human organism, right, and can't come into existence independently. But I'm also going to argue, well, we'll see, that things like cells and chromosomes and so on would also count here as integral parts. The next kind of part is a virtual part. So X is a virtual part of Y, just in case it's a material part, Y is a material substance, and X exists only potentially, right? Doesn't exist in actuality, for all of the properties, the qualities, quantities, powers, dispositions that would belong to X, this virtual part, if X were to exist actually, belong instead to Y, restricted to some sub-region of Y's location. So X, although it only exists potentially, it nonetheless has a kind of explanatory role, because its powers and dispositions and qualities have been transferred to, and are continually being transferred to, some part of Y's region of occupation, location, so to speak. So here I'm going to argue that things like bits of water, fat, protein, and so on, calcium, within a living organism are only virtually present within that organism. They aren't actually present in the way they are in the non-living world, right? So when I ingest some water into my system and it becomes integrated into me, the watery substance, which was a real substance in the inorganic world, is transmuted into a mere virtual part of me. It loses its actuality and begins to function only as a virtual part within me. Now, physical particles, protons, electrons, and so on, these are going to be usually virtually integral parts. So they're going to be both definitionally dependent on the whole substance of which they're a part, including inorganic substances, and also mostly virtual, although occasionally they'll become actualized, as we'll see. So here's a kind of a diagram to show how the Aristotelian picture works. We've got four possible kinds of parts: the actual and the virtual on the rows, the integral and the definitionally independent on the columns. And you'll notice that the upper right quadrant is empty, and that's crucial for the Aristotelian. There are no parts that are both definitionally independent of the substance and actual, right? You do have integral parts that are actual but definitionally dependent, like cells, organs, and so on, and also particles and atoms and whatnot when they are activated in interaction. And then you also have virtual parts, some of which are integral and some of which are actually definitionally independent. And this would be, examples of this would be the inorganic substances that exist virtually within a living organism. So what are the world's substances? In particular, as I said, for Aristotle, organisms are paradigms of substances, right? But are there any other substances, right? Well, yes, there have to be, because of something that philosopher Jonathan Schaffer at NYU is called the tiling constraint, which I think Aristotelians do accept. The tiling constraint says that the world is such that no two substances overlap in parts, and the whole of the material cosmos is covered by these substances. Every material thing is contained in the sum of all the substances. So this, the analogy here, of course, is to if you had tessellated floor in which the entire floor is covered with tiles, no two tiles overlap, and the whole floor is covered with tiles, right? That's the picture. The tiles are the substances, the floor is the cosmos, right? Now, I think Aristotelians cannot accept any exceptions to one, the idea that substances might overlap or that one substance might be a part of another substance. They can, however, accept some exceptions to part two. That is, there are things that I would call remnants of substances which exist, which are no longer substances, but which are nonetheless definitionally dependent upon the substance of which they're a remnant. But we can talk about that again during discussions if you're interested. Now, in particular, on my view, quantum particles are not substances and actually cannot be substances. They are never substances on my picture. There's several reasons for thinking this. First of all, there's a lack of individuality that's reflected in the quantum statistics, both Einstein or Fermi-Dirac statistics. Both these statistics treat elemental particles as mere figures in an accounting book, like dollars in the bank, rather than enduring nodes of actuality or possibility, re-identifiable as particular individuals, right? So if I went to a bank and put a dollar into my account, and it went from 1,000 to 1,001, and then I go back the next day and withdraw a dollar from that account, and I ask, did I get the very same dollar back that I put in yesterday? The question makes no sense, right? The dollars don't have that kind of individuality. They're merely parts of an account. And this is my perspective on quantum mechanics as well, that in general, particles don't exist as individuals. We just have a 2-electron system. We don't have electron here, electron there. There's just a kind of a counting entry, so to speak, for the particles. And the statistics suggest this, and it doesn't prove it, but actually in quantum field theory, the number of particles of a system, so depending upon your frame of reference, a given 110 electrons or 90 electrons. So the number of particles is actually dependent on your frame of reference, and that suggests that they can't be independent substances, fundamental substances. In every view of quantum mechanics except the Bohmian mechanics that Michael Esfeld prefers, particles lack definite trajectories or boundaries. Right? So there's not really located in general anywhere in particular. And I think that disqualifies them as substances from an Aristotelian point of view. But even in Bohmian mechanics, particles, although they have locations, they lack all intrinsic causal powers. And again, that will disqualify them from an Aristotelian point of view, because the whole point of an Aristotelian substance is to be the bearer of these fundamental causal powers. And so the matter points in Michael's system certainly can't be substances from an Aristotelian point of view. Now, let me talk about substantial form. Right, so I've talked about substance. Obviously, we need to talk about form. I won't actually say much about matter for reasons of time, but we can talk about that during question period as well. I think that Aristotle's notion of form is derived from Plato's theory of the forms. As you recall, there was a Platonic heaven in which you had the form of the good, the form of the chair, the form of so on, and then you had the various instances in the concrete world, and the similarities, the commonalities within things in the concrete world are explained by their relationship to these Platonic forms. So I think what Aristotle does is he immanentizes these forms. The Platonic forms become individual essences of substances. Forms are still involved in explaining similarity within a way. So two forms of the same kind have only derived mutual distinctness. So they're distinct from each other numerically, but that numerical distinctness is derived from the distinctness of their prime matter. It's not intrinsic to the forms themselves. And that derivative nature of their distinctness is what we can then use to explain their similarity in terms of these similar forms. So as a consequence, and again, I can explain this in question period, Aristotle's immanent forms provide an easy explanation for the structure of things like genera, species, differentia, as we see in biology or in particle physics for that matter. The Aristotelian forms are not located in some otherworldly domain, and they're not in many places at once. So they're not external to substances. There's no sort of strange metaphysical action at a distance. So there's lots of advantages to the Aristotelian picture. It was very popular for nearly 1,000 years. But this idea of substantial form was rejected in mainstream philosophy following the scientific revolution. But I think they're coming back. And if we had gotten quickly to the quantum revolution in the 17th century, we would never have abandoned hylomorphism. We would have immediately seen that it was needed, I think. So this will get us to the sort of core of the paper, which is the idea that quantum mechanics opens up a space for an Aristotelian picture. And I'm going to focus initially on inorganic substances, because they're the harder case for the Aristotelian. How do we make space for an Aristotelian, for inorganic substances in the natural world? Here I'm going to do four things. I'll talk about what I call thermal substances. It's just my term for inorganic substances in the Aristotelian picture. Then I'll explain how quantum theory, this would be points B and C and D really, why quantum theory creates the possibility for substantial form in the inorganic world as a real option for understanding what's going on. All right, so thermal substances. So as I said, a thermal substance is a material body with fundamental thermodynamic and chemical properties and only integral and virtual material parts. And I'm also going to, for this talk, I'm going to assume that the thermal substances are not organisms, right? They're not living, but they're substances in the Aristotelian sense. What makes them substances on my picture is that they have these fundamental thermodynamic and chemical properties. I'll explain that a bit later. Now, individual atoms and molecules and particles are not thermal substances. I think they never are. They're typically virtual integral parts of thermal substances. They cannot exist except as parts, or perhaps as remnants of such substances. Organisms, like you and I, have thermal substance-like entities as virtual parts. Well, we might even say they are the thermal substances, but they're existing only in potentiality in us rather than actually. Because thanks to the tiling constraint, no substance can contain another substance as a proper part, as an actual part. Right? It can only contain them as potential parts or as virtual parts. So let's turn to quantum theory. The algebraic approach, which is what I'm going to emphasize, to quantum theory brings a set of sophisticated mathematical tools to understanding the theory. And there are two kinds of models that quantum physicists use here. There are what we might call the models of what Hans Primus, philosophical chemist that I've been much influenced by, he calls it pioneer quantum theory. These are separable Hilbert spaces. And then there are the infinite models that involve non-separable systems and involve taking what's called the continuum limit or the thermodynamic limit. So I'll explain that in a minute. These two different models are very important, as we'll see. So in pioneer quantum mechanics, where we have separable Hilbert spaces, you represent a finite system by means of a vector in a single space, a very high dimensional space, where the vector represents the state of that system in that configuration space, basically, as Michael explained last time. Each unit vector in that space, whether actualized or not, represents a property, what's called a quantum observable, right, of that, a possible property of that system. And all quantum observables are subject to the complementarity and Heisenberg's uncertainty principle. So this means except when they're actually observed, they go into a state of superposition, right? In which they're a mixture of probabilities of certain positions and momenta and so on, and other more natural properties of the system. So those are the separable models. Now, why is there a problem with them? The basic problem with them is something called the Stone-Van Neumann theorem, which is proved by Van Neumann and Marshall Stone in 1931. This demonstrates that two complete representations of separable Hilbert systems have a property that's called relation that's called unitary equivalence. And a vector in such a system represents the same macroscopic thermal or chemical state, right? So there's a kind of macroscopic interchangeability of all the different possible systems within the realm of finite quantum models, these separable models. Thus, separable systems, or the separable models of systems, are useless for chemistry or thermodynamics. They don't have disjoint superselection sectors. They can't represent things like differences of phase of matter, for instance, that we'll talk about in a minute. And they can't represent spontaneous symmetry breaking, right? And this is, I think, to me, the most important part about quantum mechanics. So Michael last time said that for him, the most important thing is the lack of locality. And that's certainly a feature, but I don't think it's terribly important, actually. At least from an Aristotelian point of view, it's not terribly important. What's more important is the dynamics of the Schrodinger equation that is so linear that in finite systems, you can't have spontaneous symmetry breaking, and therefore you can't explain the kind of phenomena we want to explain in chemistry and thermodynamics using those sorts of models. So what do actual quantum chemists and quantum thermodynamics theorists use? Instead, they use non-separable quantum systems. And in those systems, the Stone-Van Neumann theorem fails. Such models have infinitely many degrees of freedom, and more importantly, infinitely many separable subsystems, right? And now we can have inequivalent representations. disjoint Hilbert spaces, right? Each with their own set of vectors, right? That can represent macroscopically distinct situations, like different phases of matter or different chemical compositions, different chiralities of molecules, and so on. And in these kinds of models, there are no superpositions of these inequivalent representations, right? So the two phases of matter never go into superposition. The two chemical compositions don't go into superposition, right? Superpositions occur only within the individual spaces, and they represent microscopic rather than macroscopic indeterminacies. So to get to these non-separable representations, what we have to do is we have to start with a finite model and then take it to the thermodynamic or continuum limit. So in effect, what we do is we treat the system, even though it's only a finitely large system, we treat it as though it had an infinite number of infinitesimally small molecules or other particles. And I think this actually fits the Aristotelian picture very well, right? Because in reality, I would say, each thermal substance is in fact a continuum of matter with no internal boundaries or discrete actual parts, right? So what we have when we have a body of water is not a bunch of individual water molecules. We have a watery goo, right, that is continuous in space. And the molecules exist only virtually within that goo. The goo can express itself in a sort of molecular way. The individual atoms and molecules are only virtual parts. Now, in physics and science in general, there's three reasons for going to an infinite limit, starting with a finite system and going to an infinite limit. The first reason would be for mathematical convenience. It's just easier to do the calculations for some reason by going to the infinite limit. A second reason would be just to isolate some factor from others, right? So, I'll assume that something is infinitely elastic or inelastic, or that the friction goes to zero by taking something to an infinite parameter. And thirdly, we can go to the infinite limit in order to introduce new structure into the representation that doesn't exist without going to that limit. And in the case of quantum chemistry and quantum thermodynamics, we go to the continuum limit for the third reason, not for the first two reasons. I think that's crucial, because when you go to a limit for the third reason, then we're using a so-called unrealistic model with, I use scare quotes here, with infinitely many infinitesimal particles, because the model captures some truth that a more realistic, again, scare quotes model, could not in principle capture, right? And this is exactly what we'd expect in the presence of substantial form. The substantial form imposes a structure, right, on the whole system that cannot in principle be explained by the parts of that system, the finite parts of that system and their spatial relationships to each other, right? The need for an infinite model represents a gap, right, in the bottom-up explanation of the phenomenon in question in chemistry or thermodynamics. Only the presence of a top-down explanans, that is the form, can explain why the finite models are inadequate, why we have to go to the infinite or non-separable models. So the use of infinite or non-separable models in quantum mechanics exactly realizes the hylomorphic model of explanation, with its inclusion of two complementary modes of explanation: the top-down formal explanation and the bottom-up material explanation. So the fact that the two models start with a finite model of the quantum components of the system in question represents the role of material causation. So there is a role for bottom-up material causation here, because we start with a finite model of the actual constituents of the system. But the fact that we have to go to the infinite limit, this unrealistic limit, so to speak, that represents the role of formal causation, of top-down causation, and both are essential in order to make sense of chemical and thermodynamic phenomena. So I'll just real briefly talk about two examples of this. One is spontaneous symmetry breaking. So in Newton Maxwell kind of mechanics, right? If I balance a pen on its edge, the pen will eventually fall one way or the other based on some kind of small perturbations of its position, right? So that it turns out actually that Newton-Maxwell system is indeterministic in a way that quantum mechanics is not. So in fact, leaving aside the measurement problem for a minute, quantum mechanics, pure quantum mechanics, is much more deterministic than Newton-Maxwell was, right? Because what happens in pure quantum mechanics is that the pencil falls in every direction simultaneously, right? So that's perfectly deterministic result, right? It doesn't fall in one direction or another, it falls in all directions. And so there's no breaking of symmetry within the pioneer quantum mechanics, these separable systems. In order to get an indeterministic result where the pencil falls one place and not another, you have to go to the infinite limit, to the continuum limit. Then you get these super selection sectors that would represent different positions that the pencil could fall into. And now you can recapture the kind of indeterminism that's required for spontaneous symmetry breaking in quantum mechanics. And once you grasp that, then you sort of see the whole picture, because in chemistry and thermodynamics, we have symmetry breaking all over the place. And so without the infinite limit, you're never going to be able to represent or understand this phenomenon. Great example here is phase transitions, right? Where you have a solid and a liquid, or a liquid and a gas. At the critical temperature and pressure, right, the substance can exist both as a liquid and as a solid, or both as a liquid and as a gas, right? And to go from one to the other is a shift in phase. That's the kind of spontaneous symmetry breaking that you can't represent in pioneer quantum mechanics, that you can only represent using the continuum limit, as I've stated before. Laura Rucci has done some really good work on this. Jeffrey Sewell, English quantum chemist, is somebody I also rely on quite a bit. You also have problems explaining molecular structure within pioneer quantum mechanics. So the Schrodinger equation for a finite system of particles is spherically symmetrical. And it's sort of hyper-deterministic. And so there's no explanation in the standard model. It's linear, right? There's no explanation in the standard interpretation of pioneer quantum mechanics for the emergence and the observed persistence of chemical structure with its breaking of spatial symmetry, right? Many molecules, chiral molecules, for example, break a spatial symmetry. And to explain that breaking, we have to go to the thermodynamic limit, right? We have to go to the continuum limit in order for that to work. So what we need, in fact, in quantum chemistry is something we could call chemical form. And the chemical form of an inorganic substance is, I think, identical to its substantial form in Aristotelian terms. So it does all the same things that substantial form does for the Aristotelian. It grounds the classification of a thermal substance by means of natural kinds in terms of its chemical composition. Again, the chemical form is not determined in a bottom-up way. You can't just give me the particles and the finite quantum system and derive from that what the molecular structure is. You have to superimpose the molecular structure on the quantum world in a top-down sort of way. So this chemical form grounds the classification of the thermal substance in terms of its chemical composition and let's say phase of matter. It also grounds the persistence of thermal substance as the same substance over time. And it grounds the substance's active and passive powers in its interactions with other thermal substances. Now, let me talk about another reason why hylomorphism is an option from within quantum physics. And that is we can restore classical properties in a logical sense to the world. And this is related to the so-called measurement problem or measurement paradox. Let's see. So Niels Bohr, quantum pioneer, right, contended that quantum theory did not exhaust reality, right? And if you look at the quantum theory at face value, that is what it seemed to be saying, right? Because the fundamental laws now, represented by Schrodinger's equation, they describe the world in terms of probabilities of certain kinds of experimental results. And the experimental results are classical results, results that we can observe in something like a classical world where there isn't superposition, where there isn't, Schrodinger's cat going into live and dead and so on. And so it looks as though at face value that the theory is telling us that the microphysical theory is not complete. It does not tell us what's going on fundamentally. The classical world is at least as complete as the quantum world. So the quantum world, as I said, didn't really make sense. The quantum theory, quantum model doesn't make sense on its own. It's not autonomous in Bohr's picture. Now, this creates a problem for Bohr, I think, because reality can't really be neatly divided in this way into classical objects and quantum objects, right? Because there are some objects that have both quantal and classical properties, so to speak, supercooled fluids, superconductors, quantum computers, and so on. But if we now introduce this insight from quantum chemistry and thermodynamics that I've been talking about, going to the continuum limit, we can then solve this problem for Bohr. When you use algebraic quantum mechanics with non-separable models, we can now distinguish between classical properties and quantal properties in a very rigorous logical sort of way, right? So the quantal properties are things that are represented by a vector within a particular space. Two quantal properties are not mutually commuting, and they go into superposition, right? Whereas the classical properties represent these super selection sectors. They represent these disjoint spaces within the model. And these they do commute with each other. All the classical properties commute with each other. They never go into superposition with each other, right? And so we can define this distinction rigorously. And so the example that I give is that of what we might call the Schrodinger's ice cube, right? So the traditional problem is, if you put the cat in the inside the box and you have some kind of quantum event occurring, which the cat is sort of measuring by either being alive or dead. If you treat the cat merely as a quantum system, then the theory tells you that the cat goes into a superposition of being alive or dead. It's neither alive nor dead. It's 50% one or the other, until you open the box and look at it. But then, of course, the problem is, again, if you describe yourself as a quantum system, you go into superposition as well. And so we never actually arrive at a definite result. The approach that I'm advocating solves that problem, and it does so not by introducing minds, let's say, or the consciousness, right? But rather these thermodynamic and chemical properties. So if we put an ice cube in the box, right, such that if the ice cube melts, we get one result. If it doesn't melt, that's another result. Then those properties are classical properties in this picture. They represent two super selection sectors. They do not go into superposition. Right. And so when the quantum system interacts with the ice cube and either melts it or doesn't, we get a definite result. Right? We don't have any kind of paradox about measurement on this kind of picture. Now, this idea has been developed more recently in great detail, actually, by physicists Barbara Drossel and George Ellis in what they call the contextual wave collapse model of thermodynamic collapse. So on this sort of picture, you have an interaction between an open quantum system, some kind of classical detecting device, and crucially, what they call a heat bath, a thermodynamic heat bath, right? And that plays a crucial role in the story. And it's precisely because the thermodynamic heat bath itself cannot be represented simply as a finite quantum system. You have to go to the continuum limit. You have to assign to it classical properties, right? In order for this approach to work. Another approach has been proposed by my friend Alex Proust up at Baylor. It's called the traveling forms model. This model works by starting really with the Everett many worlds interpretation of quantum mechanics, in which whenever a quantum event occurs, there's a splitting, so to speak, of the world into different branches, right, with various probabilities. And there's a variant of the many worlds interpretation by Jeffrey Barrett called the traveling minds version, in which there's only one actual world, at least where the minds are. So when there's a branching, the minds go off in one branch and there's no minds along the other branch. It's like a zombie branch, so to speak, right? And so you can identify which is the actual world by finding the minds in there. So it's a very dualistic picture. On these pictures, the global wave function never collapses. Now, on Alex's model, which I also like, you have substantial forms, and the substantial forms are needed to define the branches, actually. So it solves one problem that the Everett approach has. But also the action of the substantial forms determines which branch is actual. So like in the Barrett's picture, you get a distinction between a single actual world and all the other worlds that are merely potential, because the forms are only potentially there, whereas they're actually present only in the actual world, so to speak. So you get the uniqueness of the actual world, which helps us make sense of things like probabilities, which is a great problem for the Everettian kind of model. All right, so finally, let's talk about the metaphysics of both inorganic substances and then move on to living substances and rational animals here. So here I'm going to talk about the origin of, I'm going to deal with some problems involving thermal substances, inorganic substances first. their origin, their individuation. And then I'll turn to living animals, again, their origin, evolution, how we get from living organisms in general to rational animals, and then finally conclude with some advantages for this hylomorphic kind of approach. So the origin of thermal substances. Some people ask me, well, what happened at the Big Bang? I mean, in usual models of the Big Bang, you get just a bunch of particles, right? Just a bunch of photons and quarks and so on. And you're saying they aren't substances. So does that mean there were no substances at the beginning? But what about the tiling constraint, right? The world has to be composed of substances, right? So my answer to that is to say, look, that question presupposes the kind of bottom-up imperialism that I'm trying to push back against, right? So on my view, let's say that the Big Bang, suppose just to keep it simple, that we have a closed finite universe. Then I would suppose that initially from the Big Bang, you got a single gigantic thermal substance, right? Which didn't form by aggregating the particles. The particles are always only virtual parts of these gigantic thermal substances. And then as the universe evolves, this large thermal substances are breaking down into what are galaxy cluster sized and galaxy sized and solar system sized and planet sized and so on, rock sized sorts of thermal substances. So it's a process of disintegration rather than agglomeration over time. There's a lot of awkward questions you can ask me, of course, about these substances. Where does one thermal substance end and where does the next begin? Are the oceans of the earth a single gigantic watery substance, or is the Mediterranean one substance, and so on? How many thermal substances are there out there? How big or how small can they be? I've already committed myself to saying there can be really, really big. How small can they be? On my view, these are all empirical questions. And our study of this kind of collective phenomena is still in its infancy. We still don't know very much about it. I'll just throw out some conjectures at this point, right? I think that it's probably the case that thermal substances can exist at any scale, from the cosmic scale all the way down to the microscopic scale. So a thermal substance could, in principle, consist of a single particle, or even of a fraction of a particle on my picture, right? There's phenomena that are called fractional quantum effects, Hall effects. But when a thermal substance consists of a single particle or a fraction of a particle, there's still an important metaphysical difference between the substance qua substance with its chemical and thermodynamic properties and the quantal accidents, so to speak, that or virtual parts that compose it in some sense. Let's move now to living substances. So I think that this kind of approach would actually be helpful in thinking about things like origin of life studies. So instead of thinking about the origin of life as a problem about how you get a bunch of individual atoms and molecules to agglomerate into a living organism, we should instead think about how you take a single large thermal substance, or perhaps a system of thermal substances that make up the whole proto-biosphere, let's say, of the Earth, and how that disaggregates itself over time into individual substances, right? By a kind of fission rather than agglomeration. Through greater differentiation of this thing. Now, let's talk about evolution in Aristotle, right? Because of course Aristotle believed that all the species were eternal, that they weren't created or destroyed over time, and we know that, of course, that's false. But I think that was a secondary or even a tertiary part of Aristotle's system. He also thought that there were crystalline spheres that were rotating around the Earth, and you can be a hylomorphist and give up that hypothesis without any great cost, I think. So I think on Aristotle's picture, there's actually no bar to supposing that members of one species could generate members of another species, especially if on both sides we have somewhat abnormal members of those two species. And secondly, and finally, most crucially, I think, on an Aristotelian picture, animal sensation and locomotion are going to be building upon the natural powers of virtual thermal substances, right? And so this will open up the possibility, actually, for taking things like so-called secondary qualities very seriously as fundamental features of the world around us. Now, let's go from living substances to rational animals. So once we accept that there's top-down formal determination of parts by the form of the whole, we can posit that the form of the human being, which we can call the soul, determines the natures and powers of the virtual thermal substances that make up the body, right? So, and those in turn determine the properties of the quantal virtual parts that they have. So again, it's a top-down process, just iterated another level. The substantial form of a living organism helps to determine the chemical properties of its thermal substances, and those chemical forms of the virtual thermal substances in turn determine the quantal facts, so to speak, right? And so we have formal rather than intrinsic causation going on here. Now, as the soul changes through deliberation or inference, this can produce changes in the chemical and thermodynamic forms. So we do get a kind of interaction, but we don't require any direct intervention, so to speak, or interaction at the quantum level. It's rather, it cascades downward in this sort of formal way. So I don't think we're going to need a vital force. And I don't think that conservation of energy or momentum is going to be a problem on this picture. And we'll have to go into the details there about the two models. There's the model, again, the Drossel-Ellis model. On their view, energy and momentum is conserved because of the role that the heat bath plays in absorbing or contributing energy to the whole system. And in Proust's picture, there's no collapse at all. And so there's no problem of conserving energy or momentum. And so in either case, the soul can determine the indeterministic quantum level interactions between its constituent virtual parts. And then thus we have plenty of room for free will within the natural world, right? Without going to the extreme kind of neo-Kantian or almost neo-Leibnizian approach that Michael takes. Okay, I'm going to wrap up here. I hope I'm doing time-wise. Mention some of the advantages of hylomorphism. First of all, we have a greater degree of unity and integrity to the creation. This is the most important thing, right? It's not a dualistic picture. It's a much more holistic picture, right? And so on this picture, the co-evolution of body and the soul is no problem, right? In fact, evolution requires hylomorphism, I think, if biological properties are to be explanatory. If we're really going to have such a thing as reproduction and survival and so on, we need hylomorphism, actually. So in fact, evolution builds upon a hylomorphic foundation, I think. We get a real distinction here between primary and secondary causation. And so we can have God sustaining the whole thing, but God doesn't have to constantly intervene to keep the soul and body in sync, so to speak. They're naturally connected to each other. We vindicate the manifest image of the natural world. Secondary qualities pre-exist the emergence of sense organs as primitive powers of thermal substances, right? So there are chromatic interactions, acoustic interactions, osmotic, olfactory sorts of interactions among thermal substances before you even get living things. And then living things simply recruit those interactions into our sense organs so that when we perceive color and sound and so on, we're perceiving something that's really there, a feature of these thermal substances. If you reject the thermal substances, you say it's just minds and particles, then there's just no room for secondary qualities because particles can't have colors or sounds or tastes, right? But thermal substances can. And so we can reaffirm the manifest image. And we get a full incarnation of human beings. The soul is the form of the living body. And then we can, for example, explain the sacramental significance of things like bodily integrity. All right, and oh yeah, one last slide I added about God before I wrap up. First of all, this hylomorphic picture provides the basis for Thomas Aquinas' fifth way of proving God's existence, which I think is very helpful, because the causal powers of thermal substances and of organic species have to be metaphysically coordinated. So inorganic substances have to have the intrinsic potentiality of being transmuted into virtual parts of living organisms. That has to be built into them, metaphysically, so to speak, right from the very start. And substances in the early universe also have to have the causal power to generate systems of living organisms. And all of these powers are not reducible to the powers of physical interaction. So they have to come from somewhere else. And I think God becomes a very plausible explanation for that. And then I've got a few slides here. I guess we'll be able to make the slides available to you. This is some of my recent work on the project, including a new book that will, sorry, that's on the next slide. William Simpson's done work. And James Orr and I left you off there, sorry, are co-editing from Routledge that's coming forward on. I've also included some papers on the Drossel and Ellis model. And great, so I think I will stop sharing there and go back to this. I hope that worked all right. Okay.
Thank you very much, Rob.